western region of the US is home to a sleeping behemoth. It periodically stirs but hasn't awoken from its sleep in a lot of years, but when it does awaken, it may howl and heave with a power that has never been seen before. It has been 640,000 years since the beast last awoke roaring. 1,000 cubic kilometers of ash and lava were expelled during the supervolcanic eruption, which is 8,000 times more than Mount St. Helens emitted in 1980. The Yellowstone eruption area fell in on itself, leaving a 1,500 square mile buried huge crater, or caldera. The famous geysers, hot springs, fumaroles, and mud pots in the park are still heated by the magmatic energy that drove that eruption and two others that occurred over 2.1 million years ago. Now, officials at the Yellowstone National Park have discovered that a sizable piece of magma has begun to pulse. People are currently wondering whether or not this ticking time bomb will burst. Could it erupt within our lifetimes if it does? And why is a Chicago-sized portion of Yellowstone pulsing? Join us as we explore how Yellowstone National Park officials just detected a massive chunk of magma that has started pulsating. Titanic forces drive some 10,000 geothermal features deep beneath Yellowstone National Park, the animal and woodland preserve situated on a vast stretch that runs through the states of Wyoming, Idaho, and Montana. The Earth's surface has been rising and falling as a result of those forces of heat and pressure, much like the irregular breathing of a large sleeping animal. The volcano itself is actually located in northwestern Wyoming, which is where the bulk of Yellowstone is situated. An area of molten and semi-molten rock known as magma is a hot region beneath the Yellowstone supervolcano. The ground swells as magma flows into a magma chamber or reservoir that is located 6 to 10 kilometers, 4 to 6 miles under the park, and the ground collapses as the magma starts to harden and cool. Volcanologists who have been monitoring this activity since 1923 estimate that between 2004 and 2009, the ground rose by around 25 centimeters, 9.8 inches, but in 2010, the ground started to sink. Many scientists are speculating about the possibility of an impending Yellowstone eruption due to the period of gradual, continuous growth. Concerns have been raised regarding the potential intensity of the eruption if it occurs. The Precambrian period encompasses the majority of Earth's history from the planet's genesis 4.6 billion years ago to around 541 million years ago. Northern Yellowstone and the adjacent Teton, Beartooth, Wind River, and Gros Ventre mountain ranges are home to rocks that are this old. The western United States once had oceans, sand dunes, tidal flats, and huge plains throughout the Precambrian and the following Paleozoic and Mesozoic eras, 541 to 66 million years ago. The Rocky Mountains were created by mountain-building processes towards the end of the Mesozoic and the beginning of the Cenozoic. The Yellowstone region was formed by massive mountain-building, volcanism, faulting, and glaciation during the Cenozoic era, about the last 66 million years of Earth's history. On the north and east edges of the park, the Absaroka Range was created around 50 million years ago as a result of several volcanic eruptions. The current Yellowstone volcano is unrelated to this period of volcanism. The enormous swathes of today's West started to separate along an east-west axis about 30 million years ago. Around 17 million years ago, this continual stretching process accelerated and produced the contemporary basin and range topography, long north-south valleys and north-south mountain ranges, which is typical of much of the West, including the Yellowstone region. An active phase of volcanism began close to the borders of modern-day Nevada, Oregon, and Idaho around 16.5 million years ago. Volcanic eruptions that followed may be seen moving from southern Idaho to Yellowstone. The North American plate slid over a shallow body of magma in a southwesterly direction, forming a 500-mile path of more than 100 calderas. The Yellowstone region was transported nearer to the shallow magma body by the shifting of the North American plate about 2.1 million years ago. Volcanism like this is still what drives Yellowstone today. In the broader Yellowstone region, magma, molten rock from below the Earth's crust, is present near the surface. The mantle's thermal convection is the cause of this small mass of magma. Rocks in the crust are melted by magma plumes as they rise through the mantle, forming reservoirs of partially molten, partially solid rock. Mantle plumes cause hotspot volcanism by transferring heat from the mantle's depths to the crust. As tectonic plates move over hot regions, a trail of volcanic activity is left in their wake. The volcanic hotpoint that currently lies beneath the broader Yellowstone area left a swathe of volcanic deposits across Idaho's Snake River Plain when the North American plate migrated west during the past 16.5 million years. Rocks in the crust have melted due to the heat from the mantle plume, forming two magma chambers of partially molten, partially solid rock close to Yellowstone's surface. A portion of the crust above the shallowest magma chamber expanded and rose as a result of this heat. Increased earthquake activity was seen along freshly created faults as a result of stress on the crustal layer above. These faults eventually reached the magma chamber where magma began to seep through the fissures. Magma escaping the chamber relieved pressure, which also allowed volcanic gases to escape and explode violently in a large volcanic eruption. Large amounts of volcanic ash and gas were released into the atmosphere by the eruption, which also caused pyroclastic flows, rapid, extremely hot debris flows over the surrounding terrain. The land above the subsurface magma chamber sank as it emptied, forming the first of Yellowstone's three calderas. One of the greatest volcanic eruptions known to man, it covered 5,790 square miles of land, reaching as far as Missouri 2.1 million years ago. According to estimates, the entire amount of volcanic debris spewed was 8,000 times greater than that of the 1980 eruption of Mount St. Helens in Washington, which killed 56 people and thousands of animals and charred hundreds of square kilometers of land in Washington and Oregon. Around 1.3 million years ago, a second sizable, albeit smaller, volcanic eruption took place within the first caldera's western margin. The current Yellowstone caldera, which is 30 by 45 miles in size, was produced by the third and most recent major volcanic eruption 640,000 years ago. Since then, there have been 80 minor eruptions, and one of these produced what is now the west thumb of Yellowstone Lake about 174,000 years ago. The caldera floor and surrounding terrain were partially filled by enormous lava flows of viscous, rhyolitic lava during and after these explosive eruptions, as well as by less substantial basalt lava flow. The pitchstone rhyolite flow, located in the southwest of Yellowstone National Park, is the youngest of these lava flows at 70,000 years old. The majority of the continental United States was blanketed in large volumes of volcanic ash, gas, magma, and other volcanic debris from each of the prior eruptions. There have been some materials discovered as far away as Louisiana. Following each of these eruptions, the Yellowstone supervolcano fell in on itself, engulfing the surrounding terrain, including all of the trees, mountains, and other features. Calderas are the depressions created by this occurrence. In actuality, the Yellowstone caldera and Yellowstone supervolcano share the same name. In Yellowstone, a caldera-forming eruption would pose a huge natural hazard. Within the Yellowstone caldera, pressure from the shallow magma body has created two resurgent domes since the last of three eruptions that established the caldera. Sour Creek Dome and Mallard Lake Dome may both have magma as close to 3 to 8 miles and 8 to 12 miles respectively beneath them. Both domes experience uplift and subsidence as the amount of magma or hydrothermal fluids changes beneath them. The entire caldera floor also rises or falls, though not to the same extent as the two domes. The caldera floor has been tilted toward the south over the last century as a result of net inflation. As a result, Yellowstone Lake's southern sides have sunk, causing trees to now stand in water, and Fishing Bridge at the lake's northern end has risen into a sandy beach. The 50 kilometers, 30 miles wide, and 70 kilometers, 45 miles long Yellowstone caldera itself contains some remnants of the most recent eruption. In a region known as the Lava Creek Tuff, one can still observe the thick volcanic debris that was left over after the eruption. The remnant of the enormous volcanic eruption, which occurred 640,000 years ago, is a bubbling caldera in northwest Wyoming in the heart of Yellowstone National Park. The 3,472 square mile park surrounding the caldera is home to a geological paradise of bubbling pools and springing geysers, all of which are fueled by magma and extremely hot fluids that are churning in the rock below the surface. More than 500 hydrothermal features can be seen in one of these locations, the Norris Geyser Basin to the northwest of the caldera. These unpredictable geysers and pools frequently alter from day to day, but a much more significant metamorphosis has also been going on. For more than 20 years, a region concentrated around the basin has been erupting and contracting by several inches in irregular bursts. It is challenging to determine the precise origins of any given movement in a volcanically active area like Yellowstone. However, a recent scientific study might shed light on why this area of land has been inhaling and exhaling. Research geologist at the Cascades Volcano Observatory of the U.S. Geological Survey, Daniel Derision, asserts that Norris has most likely been a center of deformation for a very long time. In order to estimate what might have happened beneath Norris Geyser Basin's surface based on the changes above, researchers examined decades worth of satellite-based radar and GPS data. When a magma body intruded beneath Norris in the late 1990s, fluids trapped inside of it erupted out and moved through the rocky maze above them. The ground would inflate as the fluids became trapped and pressure built up. As the fluids were allowed to escape to other locations, the ground would deflate. Today, magma-derived fluids might be found just a mile or two below the surface of the Earth. To be clear, the new research does not suggest that the supervolcano which last erupted 640,000 years ago and formed the caldera of Yellowstone is any more likely to explode now. The tallest active geyser in the world, Steamboat Geyser in the park, has instead been erupting at a record-breaking rate since March 2018. These geologic movements may help to explain why. Researchers also hypothesize that there may be a marginally higher risk of hydrothermal explosions occurring in the basin as a result of the changes below Norris. The geology of Yellowstone is intricate and secretive, and underground explorations are especially difficult. Researchers do, however, concur that the rising and sinking ground can be explained by the injection of a sizable mass of magma and the fluids that escaped during the eruption. The scientist in charge at the Yellowstone Volcano Observatory of the U.S. Geological Survey, Michael Poland, who wasn't involved in the new research, states that we're only just beginning to understand just how dynamic Norris Geyser Basin is. In addition to the unexpected caldera deformation, a significant finding was the three-dimensional imaging of a massive magma plume or pipe beneath Yellowstone that is responsible for carrying lava and extreme heat up through the Earth's mantle. In order to observe how seismic waves respond when they pass through various materials beneath the park, researchers at the University of Utah employed a vast network of seismic sensors in and around the area. They discovered a massive 3,600 cubic mile banana-shaped body that is about half a mile and deeper and contains partially molten rock using 3D seismic tomographic imagery. This is the so-called magma chamber of Yellowstone, an irregularly skewed plume of magma that feeds the shallower magma system coming up through the Earth's upper mantle from the northwest and dropping 400 miles below is even deeper and more significant in plate tectonic theory. This significant new finding disproves past claims that Yellowstone does not have a plume and is based on fresh seismic data. Another peculiarity is that the 3D image reveals that the plume does not start 1,700 miles away from the Yellowstone National Park beneath the Montana-Idaho border, but rather 125 miles away from an important upper mantle transition zone. However, Norris Geyser Basin, which has thermal features that date back 115,000 years, is Yellowstone's oldest thermal area. It is also the hottest, with a temperature of 459 degrees Fahrenheit, around 1,000 feet below the surface. The Steamboat Geyser in the area is an example of how quickly and unpredictably this scorching section of Yellowstone may shift. The 400-foot-tall geyser has rarely erupted in the past, with intervals between significant eruptions spanning anything from 4 days to 50 years. However, since March of last year, Steamboat has erupted up to once per week. The geyser erupted 32 times in 2018, setting a record that was surpassed the following year when it erupted 48 times. Helen Robinson, a geothermal expert at Glasgow University who was not involved with the new research, exclaims, "The blinking thing went nuts." Although this mercurial geyser's hyperactivity has drawn the attention of the general public, scientists are more intrigued by the dramatic quivering of the basin itself. The Norris Geyser Basin is a dynamic place. An 18-mile-long region climbed 4.7 inches between 1996 and 2004, then fell back to 2.8 inches between 2005 and 2013. Then, in late 2013 and early 2014, the area abruptly began to rise once more at a rate of 5.9 inches per year, the highest rate of uplift ever recorded within Yellowstone National Park. A magnitude 4.9 earthquake that shook Norris Geyser Basin in March 2014 abruptly stopped the upward movement that had appeared to be unstoppable. Up until the start of 2019, the ground gradually alternated between sinking and rising. The basin has moved so much that it's now 5 inches higher than it was 20 years ago. But what, therefore, is the cause of all this chaos? Significant changes have been found in Yellowstone's extensive underground volcanic system as a result of increased scientific surveillance. The system is centered on a massive caldera that is known for its geologically rare yet huge volcanic eruptions. The Yellowstone Volcanic Observatory was established here in 2001 to improve scientists' capacity to monitor and react to changes in Yellowstone's activity. The U.S. Geological Survey, National Park Service, Universities of Utah and Wyoming, University Navstar Consortium, and the State Geological Surveys of Wyoming, Montana, and Idaho joined forces to form the Yellowstone Volcano Observatory. The observatory is an extended, instrument-based monitoring program created to track earthquake and volcanic activity in the vicinity of Yellowstone National Park. Geologists believe that the Norris Geyser Basin upheaval began between 1996 and 2001, when magma rose just short of 9 miles beneath the surface. Radar and GPS data from satellites were used to track the deformation of the basin. The basin is situated on a network of faults and vents known as the Norris Mammoth Corridor, just outside the youngest caldera of the supervolcano's northwest rim. 2 weak zones crossing one another would be a location where magma would find it simpler to enter, according to derision. The magmatic intrusion caused the uplift event from 1996 to 2004, and as the magma cooled, dissolved fluids could bubble out of it. This procedure reduced the magma body's internal pressure, causing it to deflate like a leaky balloon. Between 2005 and 2013, the ground likely descended once more as a result of this process. Since then, the ground has been rising intermittently as a result of the escaping fluid becoming periodically trapped in pockets beneath layers of rock. For scientists, identifying and documenting this cycle of magmatism and hydrothermal activity has proven to be challenging. According to Poland, the new model is a reasonable hypothesis, but it's by no means certain. According to Robinson, it's possible that sources of fluids other than the magma body, including the recent heavy snowfall, concentrate in certain places and occasionally leak out elsewhere. The team surmises that magma-derived fluids are currently present in Norris Geyser Basin just below the surface. Thousands of years old hydrothermal explosion craters are widespread in the area. They are the result of geologic pressure cookers of confined, scorching water that violently depressurize and flash boil into steam if the rock cracks, an event that is nearly impossible to predict. Major explosions are rare, but Norris Geyser Basin could experience a fresh blast at any time. Explosions caused by hydrothermal processes may be a little more likely to happen if fluids have accumulated near the basin's surface. However, according to derision, the rocky plumbing networks are incredibly intricate, with minute, imperceptible changes constantly altering the likelihood of a blast. The team does not advise banning tourists from the area because the likelihood of further explosions is still quite remote. The team also questions whether the recent record-breaking number of eruptions in Steamboat could be related to the buildup of magmatic fluids. In the 1960s and the early 1980s, the geyser experienced comparable spikes in activity that may have been related to basin breathing cycles. If this is the case, though, why does this specific geyser put on a show when others don't? Poland ponders, why not Aquinas, which is directly next to Steamboat? According to derision, the connection between the magma intrusion and Steamboat's hyperactivity is at best circumstantial, but the timing does line up. He and his colleagues intend to examine the fluids that bubble up through the surface in the future to determine if they bear the chemical signatures of a magmatic origin. Meanwhile, on the local night of August 31st this year, a 3.3 magnitude earthquake struck close to Lewis Lake in the southern region of Yellowstone National Park. So will the volcano in Yellowstone erupt once more? In the upcoming millennia or millions of years? Probably. What of the following several hundred years? How might a Yellowstone eruption appear then? Let's stress once more that there is extremely little chance of a Yellowstone eruption of any size. However, if we're speculating, a minor eruption in Yellowstone that results in lava flows and perhaps a normal volcanic explosion is the eruption scenario that is most likely to occur. As the magma rose to the surface, this would probably be caused by a cluster of earthquakes in a particular area of the park. Now, the warning indicators would be considerably more obvious in the improbable scenario of a much larger super-eruption. The entire park would certainly experience strong earthquake activity at first. Before an eruption, It might take those earthquakes weeks or months to fracture the rocks above the magma. What if we had a super eruption which was 1,000 times more powerful than a typical volcanic eruption, spewed at least 240 miles of material, lasted weeks or months, and was characterized by prolonged activity? Within the park, the lava flows themselves would be restricted to a circumference of about 40 kilometers. In actuality, only about 1/3 of the material would enter the atmosphere. Volcanic ash, a mixture of shattered rock and glass, which would be thrown kilometers into the air and dispersed throughout the nation, would cause the majority of the damage. The northern Rockies may theoretically be covered in 3 feet of ash by a super eruption, which would obliterate major portions of Wyoming, Idaho, Colorado, Montana, and Utah. A few inches of ash would fall on the Midwest at the same time, and much less would fall on the coasts. The precise distribution would be based on the season and the weather. But any of those possibilities would be awful news. That much volcanic ash has the potential to destroy buildings as well as harm people, plants, and animals. Even a few inches of ash, which is what much of the nation is capable of receiving, can ruin farms, clog roads, lead to life-threatening respiratory issues, obstruct sewer systems, and even short out transformers. And most of North America would have to stop using airplanes. A large-scale volcanic eruption would also have a significant impact on the world's climate. Sulfur aerosols released by volcanoes can reflect sunlight back into the atmosphere, lowering temperatures. The impact is just momentary because these particles have a short atmospheric lifetime, yet they can still be very noticeable. When Pinatubo erupted in 1991, it temporarily lowered Earth's temperature by around 1 degree Celsius, 1.8 Fahrenheit, and a few regions may have experienced famines as a result of the Tambora eruption in 1815, which caused enough cooling to harm crops all over the world. And compared to what a supervolcano is in principle capable of, those eruptions were really little. There are currently no indicators of an impending eruption though. Although there are still earthquakes in Yellowstone Park and the ground is still rising and falling, this is nothing unusual. The likelihood that Yellowstone won't see an eruption for centuries to come is very high. The odds of Yellowstone exploding in any given year are 0.00014%, according to the USGS, which is lower than the likelihood of being struck by a civilization-destroying asteroid. Even so, it's not a reliable estimate because there's no guarantee that Yellowstone explodes on a predictable cycle or that another eruption is imminent. There may never be another significant eruption in Yellowstone. Super eruptions will occur on Earth in the future, but will Yellowstone experience any of them? That is not a given. Yellowstone has been around for a very long time. Perhaps not even a 4th eruption will occur. Indeed, volcanoes eventually fade out. The heat rising from below and the relative cold from the surface are 2 opposing forces acting on the magma chamber beneath Yellowstone. The chamber might theoretically freeze and finally transform into a solid granite body if the heat from below is reduced. Additionally, it's important to keep in mind that the volcanic hotspot beneath Yellowstone is progressively moving to the northeast, or more precisely, that the North American tectonic plate is moving southwest over the hotspot. If enough time passes, the hotspot will leave Yellowstone's foundation, and the supervolcano there will presumably cease to exist. In fact, a second supervolcano could form much farther to the northeast, but that wouldn't happen until the hotspot warmed up and melted the crust, and it can take 1,000,000 years or longer for that to happen. It's difficult for us to comprehend something like 1,000,000 years. The human species is a recent one. However, these systems take a very long time to operate, and Earth has been around for a very long period. Geologists have discovered evidence of at least 47 super eruptions throughout Earth's history. Therefore, Yellowstone is not the only supervolcano in the world. The most recent took place about 26,000 years ago at Lake Taupo in New Zealand. More significantly, tectonic plate movement led to the enormous Toba eruption that occurred 74,000 years ago. According to others, that precipitated a 6 to 10 year global cold and may have all but wiped off the pre-human race. Although it's not an unbreakable rule, the Earth has typically experienced one super eruption every 100,000 years. Let us know what you think in the comments section below.